Hello, it's Stat 135, Lecture 30. Last time we started section 12.2 in NOVA. Here we're testing that the differential effect alpha I for each treatment group is 0. In other words, that all the groups have the same mean. For example, if you have 7 labs measuring the amount of malleate and each group has an average amount of malleate, and there's a total mean mu for among all the 7 labs, and we can measure the differential effect for each group. That's our alpha I here. Our null hypothesis is that each of these alpha I is 0. In other words, that all these groups have the same group average mu. So we talked about this important identity. The sum of squares total is the sum of squares within plus the sum of squares between. There is an algebraic proof in the book, but I think it's more instructive to look at a 3, I is 3, j is 3 example, the one that I gave. We showed that the identity holds in that case, and furthermore, that SST over sigma squared is a chi squared ij minus 1, and SSW is over sigma squared is chi squared ij minus 1, and SSB over sigma squared is chi squared I minus 1. Today we're going to talk about the F distribution and the F test. We'll talk about the F test for different size groups, and we'll introduce the Bonferroni method for multiple comparisons. So the F test is a friend from Chapter 6. Chapter 6 is about normal theory, and chi squared t and f are all distributions based on the normal distribution. So the definition of the F distribution with two parameters a and b is that it's a chi squared with a degrees of freedom divided by a chi squared with b degrees of freedom divided by b. So we can apply that for our situation. So here we're going to essentially be having our F test is going to have test statistic and F distribution with our two parameters a being I minus 1 and b being I j minus 1. So that's essentially it's essentially SSB over SSW, and so yes, in fact, the F test is SSB over I minus 1 divided by SSW over I j minus 1. And given the example from last time, we would have gotten an F statistic of 12. So 12 with degrees of freedom, I forgot what it was, 6 and 2 or something like that. 2 and 6, yes. So now, what does 12 mean? So if the null is true, your F statistic should be around 1. If the null is not true, the F should be larger than 1, and that actually follows from page 481 in Rice, and I'll let you read this here. So the F distribution looks like something like this, and if the null is true, so this is the null distribution, assuming the null is true. So it should be centered around 1, and we're doing a one-sided test. You're going to get, in this case, 12, and if that's less than the critical value, you would reject the null and conclude that at least one of the groups at least one of the groups has a differential effect, or in other words, at least two groups have different means. So we introduced the ANOVA having the same treatment group sizes, but that's not necessary. All of what we've done can be extended for different size groups, and the degrees of freedom for SSW and SSB are are what I've shown here for SSW. It is now summing I from 1 to I, ji minus 1. And for SSB, it's still I minus 1 because you still have I treatment groups. That doesn't change. So I've written out here the sort of updated F-test formula allowing for different treatment group sizes. If you're curious about how the example that we did last time would change if we had different size groups, in the appendix to these notes I've included those details in purple. So the assumptions that we have for our F-test is that our data Yij be normal. The variance of each treatment group is the same sigma squared, and all observations are independent. If you don't satisfy these, then you should be doing a non-parametric test that we'll do next time. So now let's talk about the Bonferroni method for multiple comparisons. So doing an F-test and rejecting the null allows us to conclude that at least one of the alpha i's is not zero, or equivalently, that not all groups have the same mean. However, it doesn't tell us which group has a non-zero alpha I, or equivalently, which two groups have different means. So to answer this question, what you don't want to do is a whole bunch of t-tests, all with level alpha significance. So what we want to do instead is decrease the level of significance for each of those t-tests. And so there are different ways to do this. Let's let n, here I should write this here, so let n be the number of treatment groups. Okay, so then what we're going to do is, if we wanted to make n choose two simultaneous confidence intervals, each confidence interval should be a alpha over n choose 2 level significance. And I'll explain why in just a second. By the duality of confidence intervals in hypothesis testing, each confidence interval corresponds to a t-test that two groups have the same mean. In other words, the difference of their means is zero. The chance that at least one of these CI doesn't contain zero is less than or equal to alpha, and let's see why. So let alpha ij be the event that groups I and j don't have the same mean if the null is true. So the union for I less than j of aij's is the event that at least one of ij of the groups don't have the same mean. So by the addition rule, this is less than or equal to the sum of the probabilities, because these alpha aij's are not all mutually exclusive. So now the probability of each aij, as I said, is going to be alpha over n choose 2, and there are n choose 2 of terms in this sum, so the n choose 2's cancel and you just get alpha. So now if I is 7, this means doing 7 choose 2 or 21 pairwise t-tests with significance level alpha over 21. That's a lot of work. So for what I suggest we do is a shortcut Bonferroni method, which would allow us in this case to only calculate 7 confidence intervals. Here's how it goes. So what we're going to do is we're going to let AI be the event that we reject the null, be the event that if we reject the null, that the ith group has mean mu. So what we're going to do, so AI is the event that we reject the null, that the ith group has mean mu. And we're going to make I simultaneous confidence intervals, each with level significance alpha over n, and we're going to pairwise compare these CIs. Okay, so your confidence interval is what you're testing here is that the null of the ith group is the group mean. The mean of the group is the group mean. So what we're going to do is we're going to do pairwise comparisons of these confidence intervals. If two of these confidence intervals don't overlap, it's unlikely that they share the same mean, right? So each confidence interval is, let's say, a 90 is a certain chance that the group mean, the true group mean, lies in that. Sorry, let me rephrase that. So the confidence interval is a certain chance, gives it certain chance that interval contains the true group mean for that group. And so if you have two confidence intervals that don't overlap, then it's highly unlikely that those two groups share the same mean. Okay, if they do overlap, then there is, there's a chance that they contain the same mean, because that mean would be in the intersection of those two overlaps. Cool. So let's take a look at an example. So here we have three treatment groups. So here we have three treatment groups. Let's say alpha is 0.3. We're doing a two-sided t-test here. So actually, the level of significance for each confidence interval is going to be alpha over 6, which is in this case 0.05. So the cutoff for n minus 1 degrees of freedom is 0.05 is 2.92, and so I can set up my three confidence intervals, and great. So I have set up these three confidence intervals here, and I can look at a histogram, and what you can see here is that the first and the third group confidence intervals do not overlap. So it is unlikely that they have the same mean. Now, group 1 and group 2 do overlap, so it is possible they have the same mean, and group 2 and group 3 overlap, so it is possible they have the same mean. But we would be led to conclude that group 1 and group 3 do not have the same mean. So this is a sort of quick and dirty way of doing a Bonferroni method that saves time. Have a great day. See you next time.